Hey Simon,
Hey,
how's it going? I feel like I haven't heard from you much this semester.
um, yeah, uh, all right. How are you?
Doing fine. Yeah, yeah. Well, what classes are you taking?
I'm taking this class, um, complex analysis, algebraic topology, and I'm also reading Harshon.
Oh, okay, nice. So yeah, it's like the two standard qual courses and then Hartshorn in this. Okay. How far are you in Hartshorn? How's that going?
Very slow.
Yeah, that's Hartshorn, right? It's,
Yeah, I'm on sheaf of modules now.
oh, very nice. Cool. Wondering, I don't know how your first year has been so far, but hopefully it's been okay. Uh,
Um, I would say it's been okay.
yeah, good. I'm happy to hear that. How's it going, Freddie? Mr. Haircut?
Yeah, I think this is the least bad pandemic self haircut I've given.
Nice.
Yeah, it's going all right. How about you?
Yeah, yeah, I'm doing all right. Doing all right. Yes, I still have to read the email we got for the
Mhm.
ad paper. So we can discuss it at some point.
Yeah, definitely.
Hey, oh, Freddie's
Hey.
got the haircut that I need. Huh?
I've finally gotten used to giving myself bad haircuts. It's great.
Oh, no, I go to
Mhm.
a one-on-one hairstylist these days. So it looks good, looks really good until it doesn't. I feel like if you get a really good haircut, then all of a sudden you get sensitive to the fact that it's starting to get a little long. But yeah, yours looks good.
Thanks. I've had practice.
Yeah, straightforward, nothing wrong with that.
Yeah.
Yeah. All right. Yeah, we had an exciting weekend on the referee report front. It's funny how you hear like nothing for months and months and months, and then you hear about two papers on the same weekend. It's ridiculous. All right. Makes me feel that much guiltier about the referee reports that I still have to turn.
Well, it's ridiculous, but in a good sense, right?
Yeah, sure. Mm-hmm.
It was funny how just on Thursday, right, you were saying that you like laughed when your girlfriend was like, "Oh,
Mm-hmm.
have you heard back yet?"
Mm-hmm. 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 I was like, come on, it's only been 3 days. It was 6 days. Come on, yeah. No, she was happy to know. Yeah. Anyway, yep. And actually, there was like more information in the 6-day report than even, or the editorial thing. Anyway, whatever. Okay. Pardon me while I chew. I should stop doing that. Yeah. Are there any questions? All right. Well, you probably know what we're doing. So in the last lecture, we had a very exciting motivation for Lubin Tate's approach to, it's not just local class field theory, it's explicit local class field theory, in the sense that, again, we're not just giving you some topological group and in some sense, constructing in some sense a homomorphism from the profinite completion of that topological group to the abelianized Galois group of your field. We are actually giving a sequence of kind of elements. We're giving a sequence of elements that together generate the maximal abelian extension of K over K. Okay. Yeah, and then in particular, when K is QP, we should be able to deduce the local Kronecker-Weber theorem, which is to say that the maximal abelian extension of QP is attained by adjoining all roots of union. As is true for Q, which we'll see later in the course. I hope. I think it looks like we have time for it. It's true for Q. It's true for QP. It's not true for any other. I guess there's some version of it which is true for if you take a rational function field, then there's a kind of there's an analog of cyclotomic function fields. They can't literally be cyclotomic. This is a good callback to the previous course, the algebraic curves course, because of course, if you adjoin roots of unity, those are constant extensions of the function field, constant extensions of a perfect ground field. So those fields would be everywhere unramified. So if you adjoin all roots of unity in the function field case, you will precisely get the maximal unramified extension of the field, which is nothing compared to the the maximal abelian extension. But then there are some close analogs to cyclotomic number fields. Anyway, whatever. Okay, so there are these Kronecker-Weber theorems sort of over Q and over QP. Okay, well, I just want to go into it. So today I want to begin with a review of formal groups. It's a little bit ironic because generally when I teach the first course on elliptic curves, I kind of bail out on the chapter 4 of Silverman, the formal group stuff. Not because I don't like it, just because you don't really need to do a whole chapter on formal groups to deduce the consequences that you need to study elliptic curves over local fields. For instance, if you follow Cassels' book on elliptic curves, he does it just much more quickly and simply. And in a first course on elliptic curves, you kind of need all the time you can get. Do I like formal groups? Are formal groups important when you're studying abelian varieties over local fields? Yes and yes. Okay, and so I guess you've seen by the time I get to the second course on elliptic curves or abelian varieties, which I taught last spring, was it? It's all really running together. Then I say, oh well, everybody knows about formal groups, so I don't cover them, and then I use them. That's the way to do it, right? Okay, but now I'm going to start from scratch, so I will introduce them in a particular context. So yeah, I'm following Harari, who was following the 1965 or 1966 Annals paper of Lubin and Tate, which is a pretty short paper. His chapter is longer than the paper. And then the year before, though, there is a solo paper of Jonathan Lubin, which is about just about sort of the finer structure of formal groups over a local field in our sense, and that's an interesting paper too. Okay, so I'm going to kind of do a little bit, which is slightly in the spirit of Lubin's earlier paper, but then we'll just get off with the Lubin Tate business. Okay. So yeah, review ? Of formal groups. See it again for the first time. So we can work over an arbitrary commutative ring. The theory will be really, if we were doing formal groups over a field of characteristic 0, then the answer would be like they're all isomorphic to each other. So the more complicated the ring, the more complicated the theory. So first of all, there's some formal power series stuff going on. So I had to choose this notation is slightly different from what is in Harari. So if I have two formal power series in any number of variables, doesn't really matter, we're finitely many for us. Then if I write f equals g plus O of k, really what I mean is that f minus g is in the kth power of the maximal, well, it may not be maximal because the kth power of the ideal generated by the indeterminates x1 through xn, which I guess is maximal if and only if R is a field. But yeah, so the idea is that you just write these things out, and so if I so they're equal up to terms of degree k or larger. Okay, so that's what f equals g plus O of k is going to mean. But again, you should really think of it as congruence modulo the kth power of the ideal generated by the indeterminate. Clearly the same thing. Okay. So here we go. Here's the basic definition. A one variable formal group law over a commutative ring is a formal power series in two variables with coefficients in R, and it satisfies the following axioms for which there's a lot of dependencies. This is very far from an independent list of axioms, which is good, as I'll remind you in a second. So you have this formal associativity law. Yeah, maybe I should remind you guys, we're going to be doing some power series operations, and one of the things that we're going to be doing is substituting formal power series into other formal power series. that is totally fine and good. You know, you can compose formal power series whenever, whenever it seems like you should, as long as the power series have 0 constant term. Okay, what do I mean you can do it? I mean, it's just well-defined as a formal power series. If you expand everything out, you see that you get a well-defined formal power series. You know, in complex analysis, you could plug in one power series into another power series, but then if you look at what you get, you would have to use convergence even in order to make sense of it. Okay, so you just think for a second, but like if you try to do like e to the x, it's not defined as a formal power series because you collect coefficients of one term and you'll find that you have infinitely many coefficients to add together. So that doesn't make sense formally. But if you did, you know, I don't know, now I'm trying to remember which way it goes. If I did sine of x, then that would be formally defined. Okay. Anyway, so right, so we want this kind of associativity. It sort of looks like the associativity. We want these kind of identities. So if you plug in 0, if you set y equals 0, you should get x. If you set x equals 0, you should get y. Maybe these aren't even, this one is kind of one of the most important ones. This maybe I should say this one first. So sort of, it should be equal to x plus y plus higher order terms. Okay, so this is the first one and the fourth one are the most important by far, as I'll mention. So this is like, you know, it's like x plus, you can think of it as being some kind of deformation of x plus y. Okay, so, you know, it definitely starts out that way. That's the linearized version of it, is x plus y, and then there's some higher order correction terms. Okay, and then there's this property that there should exist a unique one variable formal power series, which we think of as the inverse, in the sense that f of x comma iota of x is identically 0 as a formal power series of x. Okay, so these are a one variable formal group law over commutative ring R should satisfy all of these things. And then we also say that the formal group law is commutative if you interchange x and y, then you get the same formal power series. Yeah, so these axioms are very far from independent of each other. I'll make these exercises. These are fine exercises, actually. But in particular, they occur in Silverman. So yeah, so for instance, if you only assume FG1 and FG4, you may even be able to assume one for one of these and one for the other ones. But okay, suppose you assume associativity and this x plus y plus O of 2, 1. Then already you can show that there's a unique inverse. Okay, and then what that inverse also works the other way. And again, it's one of these things where, like, if I try to tell you how to do it, it's not going to work. If you think about it without writing it down, you might get really confused. And then if you just write it out, you're going to discover that everything is set up just right so that you have some infinite sequence of equations that has a unique solution. Okay, so, you know, it really is not obvious to me as I'm looking at it that this works, but as soon as you write it down, you will get it. Well, it can take a few minutes or whatever, but you'll get it. And then secondly, again, this other axiom. Okay, so the first and the fourth one imply the second and the third one. That's good. So by the way, that's not nothing. If you're trying to prove that something is a formal group law, okay, you only have to check the first one and the fourth one because the second one and the third one follow. What about commutativity? I think actually that it's not a big deal, but I think that Harari says the wrong thing. I think Harari says that one-dimensional formal group laws are always commutative. That is not precisely true. It's almost true. So here is a standard example. So this ring is the ring of dual numbers over FP. Okay, so, you know, two-dimensional FP algebra, non-reduced. And so if you just take x plus y plus your nilpotent element times xy to the p, it's not much of an exercise. It's either true that this very finite formal power series, that's a little bit lucky, right? So all you have to do is check that this thing satisfies these four axioms, but okay, it's obvious that it is not commutative, right? So yeah, so apparently you do get a formal group law over this kind of weird ring. Okay. I mean, it's not the craziest ring I've ever seen, but it's not, I wouldn't call it a great ring either. And so here's the precise result, which I found. So there's a whole book on formal groups by Mitchell Hazewinkel, which is a nice book. So page 38. So if you take, for a commutative ring, the following are equivalent. Every one-dimensional formal group law is commutative. That'd be great. So what's the equivalent condition? That R has no non-zero torsion nilpotence. So what is a torsion nilpotent element? It's an element that is like additively torsion. So it's killed by multiplication by a positive integer, and it's a nilpotent element. Okay, so obviously 0 is a torsion nilpotent. And so yeah, so this is a great example of a ring. Epsilon is because it's FP, everything is P torsion. And so yeah, so this is precisely a ring in which epsilon is a non-zero torsion nilpotent element. And so the result is as long as you don't have, if and only if you have no non-zero torsion nilpotence, then every formal group law is commutative. So in particular, as long as your ring is reduced, then you have every one-dimensional formal group law is commutative. Spoiler alert, the rings that we care about are going to be a discrete valuation ring. So great, it's a domain, it's reduced. Okay, so for us, sure, all formal group laws will be commutative. Okay, let's give you a couple examples, not very exciting examples, but useful ones. So the first example is, I was telling you that this fourth axiom is saying that the formal group law is kind of like a deformation of the additive group. Well, in particular, it's kind of clear that you could take f of xy just to be x plus y. That's going to satisfy all the axioms, right? It's going to be a commutative formal group law. By definition, that is the additive group. Okay. Here's another one, x plus y plus x times y, also very simple. Why is this called the multiplicative group? Well, you do this little maneuver and you see that it's really x plus 1 times y plus 1 minus 1. So, you know, f of xy equals x times y is just not allowed, right? Because it has to start x plus y. And so the idea basically is that this group is should be doing the group law should be multiplication, but we're kind of translating the multiplication where the multiplicative identity is 1 back to 0. So the way to think of the multiplicative group is that you really want the group law to be xy, but you can't. But then you conjugate this by the translation x goes to x plus 1. Right? That's okay. That's what it is. This is xy conjugated by x goes to x plus 1. Okay. So yeah. All right. So those are the two most important examples of commutative one-dimensional formal group laws. Yeah, so by the way, one of the results that we don't need because we're not working, if one of the results, basic results, is that I will define homomorphisms and isomorphisms of formal group laws coming up. And so one of the basic results is that over a field of characteristics 0, every formal group law is isomorphic to the additive formal group law. Okay. And that is really not true over a field of characteristic P, and you're starting to get at the theory of formal group laws by this is like, if you've ever heard anyone say like p-adic logarithm, then it's very relevant here. Okay, so one thing, so formal groups, it's like again, there's various ways of saying formal groups. There are very scheme theoretic ways of saying formal groups if you really want to. And maybe I'll say that, I can't remember, maybe I say this later. I do say this later. Okay, so I make my one scheme theoretic remark. But the idea is like a formal group is like the algebraic shadow of a group. It's kind of like a group law. It's telling you how to multiply elements together, but where are the elements? But there can be elements. If you take a complete local ring with max, so complete means again that the natural map from the ring to its amatic completion is an isomorphism. So for instance, hey, great, the ring, a complete discrete valuation ring is certainly an example of the simplest example of it's precisely a regular one-dimensional complete local ring equals a complete discrete valuation ring. So yeah, so in such a situation, if you have a one-dimensional formal group law, then you can sort of plug it in and get an honest group. So what does that mean? I'm going to write f of m. And so the underlying set is going to be the maximal ideal. Okay. And now I'm just going to plug in points. I'm going to define this addition on the maximal ideal relative to the formal group law to be what you get by plugging in the formal power series. Okay, so notice if the formal group law were the additive group law, this would be the usual addition, and the group that we would get would just be the additive group of the maximal ideal. In general, it's a different group law. How do we know it converges? Well, that's where it's really nice to know that R is complete. Okay, so there's various ways of, you could even say this, there is an M-adic topology, and you're going to get like a Cauchy sequence in that. Anyway, you don't need to say it this way. If I were very French, I would start talking about uniform structures and Cauchy nets and filters and uniform structures. Too much, but it's pretty clear that this thing is one way. The algebraic way of thinking about it is that if you try to plug this in, which is if you plug this in, I get an infinite series. Okay, I can definitely make sense of what this infinite series is modulo every power of the maximal ideal, because that just involves truncating it at a certain point, right? And then when I pass from R mod m to the n plus 1 to R mod n, all I'm doing, if I go from truncating it after n terms to truncating it after terms of degree n to truncating it after terms of degree n plus 1, then truncating it after whatever I get after truncating it after terms of degree n plus 1, if I map that back down to R m to the m, then I'm going to get a compatible inverse system. Okay, so just if you take like f sub n to be the one that the element that you get by stopping after terms of degree n, then f sub n is an element of is going to give you an inverse system, and therefore is going to define an element of the inverse limit. But this map is an isomorphism, so it defines an element of R. Okay. That's the algebraic way of saying it. You could say it more topologically if you wanted to. Okay. For that matter, it is often useful to do so. You don't just have to plug in the maximal ideal, you could plug in any power of the maximal ideal. Okay. And so yeah, for me, this is the beginning of like p-adic Lie theory or something. So this is a very, very useful and reasonable thing to do, especially when you're studying abelian varieties, or if you're studying a commutative algebraic group over a complete discretely valued field, then you really do want to think about this. This is telling you very important information about the structure of the kernel of reduction. Okay, just to say it. Okay, so just for some examples, again, if you plug in the additive group, you'll get if you plug in m to the n, then you'll get the additive group of m to the n. If you plug in the multiplicative group, then again, f of xy is 1 plus x, 1 plus y minus 1. So again, this is a help. Also, how do we think about the multiplicative group? So again, the multiplicative group is like multiplication, but kind of translated back to 0. So when you plug these things in, 0 is still going to be the origin. Maybe I should have said that. So the 0 element of m is going to be the origin of the group law, but it's supposed to be the multiplicative group. So the map from this formal group, when you add 1 and you look at what the formal group law is giving you. So adding 1 gives you a group homomorphism from whatever group we just defined to the multiplicative group m plus 1. Okay, which again, we've seen this. This is like the first higher unit group that we were studying, right? These are m plus 1 is the set of things that reduce to 1 modulo the maximal ideal, okay, which is a subgroup. Okay. right? And so similarly, if you plug in m to the n, then you get 1 plus m to the n, and this is the nth higher unit group, things that reduce to 1 modulo the nth power of the maximal. Okay, so this is all very, like, there's no question that this is a very reasonable, relevant thing to be looking at. Okay. Yeah, so the filtration on the unit groups that we've considered, just in general, you consider when you're studying local fields in particular, we've considered for various purposes. That filtration on the unit group is the natural filtration that you get on the multiplicative group. Okay. I don't know if I can't remember, maybe I didn't say it, I guess I don't need it. Just like you have on your higher unit groups, the successive quotients are isomorphic to the additive group of the residue field. That's actually true for any one variable formal group law over at least over a complete discrete valuation ring. That's going to be true. If I take the formal group law, plug in m to the n, mod out by formal group law, plugging in on m to the n plus 1, Silverman does this. You're going to get the additive group of the residue field. Okay. So this is not just a group, it comes with a canonical filtration by subgroups whose successive quotients you understand. And somehow the question is, how is this, again, in the case where the residue field is finite, each of the successive quotients is finite, but this is a big infinite group. So how is this big infinite group being put together out of the successive quotients? Okay, and here comes the scheme theoretic remark. So if you take a smooth group scheme over R of dimension n, then to this you can associate an n-dimensional formal group law. So that's also a thing. I'm just looking at the one-dimensional case. An n-dimensional group law would be a vector of n formal power series, each one in 2n variables, and the definitions would be kind of similar. We only need one-dimensional formal group laws here. But yeah, and so this is, and again, in the case of an elliptic curve, Silverman explains, how
Can you by chance move the page up?
Yes.
Thank you.
Yes, I can. Okay. Right. And so this is in a certain way that the formal groups that I'm going to define here do not come in a natural canonical way from honest group schemes. So I don't need to review it in detail, but you should definitely understand. I mean, this is real Lie theory. Like, so if you have a group scheme, then the formal group law is somehow capturing the group scheme in an infinitesimal neighborhood of the origin. That's the intuition. What does that actually mean? Well, that depends on the definition of a formal scheme, which I don't need to go into. But roughly speaking, you're doing some kind of on the level of a, if I had an affine group scheme or something, or if I had an affine coordinate ring, roughly speaking, I would be completing the local ring at the origin. Okay, that would give me the formal scheme, and then sort of by functoriality of completion, the group law should induce some kind of something or other on the completed local ring, and that's where this formal power series is coming from. Okay, so I mean, again, it's in a different course, one might want to understand this passage from a group scheme to a formal group law. Yeah, it's really important in the this really is Lie theory. So there's somehow, if I have a group scheme, I can attach its formal group, and I can also attach its Lie algebra. In fact, and the formal group is remembering kind of all the infinitesimal information, and the Lie algebra is only remembering like the linear information. Okay, so this is intermediate between the group scheme or the Lie group. If you could also do this, I guess I'm saying it in scheme theoretic language. You could also do this if you had an analytic group in a reasonable sense. And then yeah, so this is intermediate in information between the actual group and its Lie algebra. Okay. And by the way, so yeah, so I really recommend, Sarah has some lecture notes on Lie algebras and Lie groups, and he explains this kind of stuff. Maybe not for group schemes, but for analytic groups. Okay. but a group scheme would give you an analytic group. So, okay, fine. Over the right kind of, over R, if R is a complete discrete valuation ring, it certainly would. Okay, well, we don't need all that. That was just for culture. Coming back to reality. So if I want a category, by the way, right? So I really do want a category. So one-dimensional formal group laws are going to form a category slightly better, just for the categorical properties, I guess. You'll see in a second. All formal group laws, if you commute a formal group laws, arbitrary dimension would give you a slightly better category. It doesn't really matter. Okay. So what are the morphisms? A homomorphism of formal group laws, it looks a little bit strange at first. So it's a power series. F equals O of 1 is my fancy / weird way of saying there's no constant term. Okay. One variable formal group, one variable formal power series, which really is, satisfies this formal homomorphism property between F and G. Okay. So that's a homomorphism of formal group laws. Right, so yeah, this is the end of my discussion of formal, just general stuff on formal groups for now. Right, and so by Hom f of G, I mean, for the moment, the set of homomorphisms between those two formal group laws, as I just defined. Now I can define a sum of two homomorphisms, but it would probably be safer to use a different symbol, okay? Because by the way, F and G are formal power series in one variable, right? So F and G canonically live in a ring. So you might think that F plus G would just be to add up the formal power series. Well, that's what it is if both formal groups are the additive group, but in general, it's not. In general, by the sum, I mean use the target formal group to add them together. Okay, and that's sort of the right thing. If you think of a formal group as actually being the law for a group, but you have to plug in the points, then how do you add two homomorphisms from a set into a group? You don't even need the group law on the first thing. You only need the group law on the second thing, because how do you add them? You add them pointwise. Okay, and that's what we're doing. We're adding F and G pointwise in G. Okay, which has scare quotes, but again, if I had a complete local ring, then I could plug in and it would literally be adding pointwise in G. Okay, so that's how I add two homomorphisms. And so then if I have, if I have F, which is a homomorphism from F to G, and then I have G, which is a homomorphism from capital F to capital H, then I can give you a composite homomorphism from F to H. And this time the composition literally is the composition of formal power series, okay, which is well defined because F and G have no constant term, okay? And I guess there's an exercise here, which is to check that if F is a homomorphism here and G is a homomorphism here, then literally just the composition of formal power series gives you a homomorphism here, okay? It's true. And so therefore what, yeah, so again, I was about to write, it's funny actually, because when I was first writing these notes, I wrote, therefore one-dimensional, we don't want the formal group laws to be non-commutative, so let's just say they're commutative, and for the rings that we're going to consider, that's going to be automatic for sure, as I just said. So one-dimensional commutative formal group laws, I wrote forms an additive category, which, what is an additive category? It means that the Hom sets are not just Hom sets, the Hom sets should be commutative groups, and the composition should be bilinear. Okay, and then I looked that up and I was like, wait, is that the definition of an additive category? And it isn't nowadays. That's the definition of a pre-additive category. I don't know, it totally doesn't matter at all for our purposes, but does anyone know what is the extra juice that you need to be an additive category instead of a pre-additive category? Tyler looks like he's saying something, but we can't hear him.
I'm just reading the wiki page on this.
Okay, great.
Yeah, you need to also admit finite biproducts.
Yeah, so you want by a byproduct, you mean something which is simultaneously satisfies the universal property of the direct product and the direct sum. And so yeah, and so we don't have products for the stupid reason that, you know, the product of two one-dimensional formal group laws should be a two-dimensional formal group law. So that's the point. If we included, if I didn't just restrict to one dimension, so this would be like saying, commutative group schemes over R should also form an additive category, but they do. But one-dimensional commutative group schemes do not form an additive category because their product won't be one-dimensional anymore. Okay, totally. So I was like, oh, my bad. Let's call it pre-additive category. And then after I worked this out, I was a little like, I was kind of figuring a little bit of this out for myself, and I was a little bit not confused, but it was taking me a little while to work it out. And then I found this paper of Jonathan Lubin that I mentioned that comes right before his paper with Tate. And he writes it out. He's probably a graduate student when he wrote this paper. He writes it out very, very, very nicely, all this structure. And then he's actually examining the Hom structure as most of what he's doing. And then I really laughed because he says one-dimensional commutative formal group laws form an additive category. So I guess the definition of what an additive category was got changed slightly since 1965. Anyway, right. So if I took out the one dimension, then it has finite products and it would be an additive category. Okay. More importantly, as for any additive category, okay, so an additive category means the Hom sets have the structure of a Z module and the composition is a bilinear Z module map. Okay. Even better, as always happens when you have a pre-additive category, if by end of F you mean Hom FF, well, I just told you how to add and I told you how to multiply. And so in any pre-additive category, the ends form a ring. Okay, and this is why pre-additive categories are really nice, right? So again, just again, other examples like elliptic curves over a field form a pre-additive category, and the endomorphism ring of an elliptic curve is a very natural and important object, by the way, especially for me, right? And so therefore, these formal groups have endomorphism rings. Okay. If you want to be slightly more fancy about it, which does come up, the like slightly categorified take on this is that Hom FG has the structure of an end F NG bimodule. Always true on that. There's no additional con. All I'm just saying is if you're in an additive category and you have two different objects, you look at the Homs between them. You can't multiply them because that's not the way the categories work. However, you can compose with an endomorphism on the source, and you can compose with an endomorphism on the target. And if you want to be fancy, that's a bimodule. Okay. This is it's not a big deal, but this is actually, there's something that comes up later. Now I'm thinking probably not in this lecture because we're not going to get to it, but this bimodule structure is a naturally occurring thing. Okay, and then the end of this discussion. So we have the notion of a formal R module is if I have a homomorphism from R into the endomorphisms of my formal group. This is just a definition to be seen. I mean, at the moment, like I could do this, like, why is R equal to R here? It's not clear. In general, like if I wanted to say, formal S module where S is a ring, then I would mean a homomorphism from S into the endomorphisms of my formal. Okay. So that's okay. Right. And again, you see it's formal because this is not actually a commutative group, but something that sort of acts like a commutative group. But one more time, if your ring is a complete local ring, then you plug it in, and a formal R module structure, and again, R doesn't have to equal R. Formal S module where S is some, let's say, commutative ring. It's not even, doesn't even have to be commutative ring, where S is some ring. If you have a formal S module structure and then you plug in points, then the FM points of your formal group are not just going to be a Z module. They're going to be an S module if you have such a structure. I mean, of course, like there's not much content into what I'm saying. You have to tell me how I'm going to give a ring homomorphism from some ring into the endomorphism ring of my formal group, and that's exactly where Lubin-Tate theory begins. And in fact, that's where what would like to happen in the rest of this lecture, but I think maybe it's going to take a little while. By the way, the endomorphism ring does not need to be commutative. And what is Jonathan Lubin doing in his solo paper? He's looking at one-dimensional formal group laws over even a characteristic, just the ring of integers of a p-adic field. That's his R. And then he studies what these endomorphism rings are, and he studies some formal R module stuff. Okay. Any questions? Yeah, I mean, maybe just one example. If the formal group is the additive group, oh, so we always have, of course, because, oh yeah, so there is one thing to say here. Right? So for just because this is a ring, I have a canonical map from Z into n of f, so I take n and I map it to. This is called multiplication by n, but of course, it's just, if this is actually a ring, whatever, it's just 1 plus 1. Or the inverse. But yeah, if you believe that this is a ring, then of course I take n to n times the identity element of this ring. And so therefore, whatever the endomorphism ring of my formal group is, I always have multiplication by n maps on my formal group. And if you just stop and think about this a little bit, like this, the structure of the formal group really comes in. So suppose, for instance, that that I was working over, maybe R is a formal power series, is the ring of integers of a Laurent series field in positive characteristics. So it's like FQ double bracket T. What's going on here? Again, if the formal group is the additive group, then multiplication by n, yeah, so okay. Multiplication by n, this is an endomorphism, so it's a one variable power series. Guess what it is? It's actually nt. Okay, so I mean, on the additive group, this multiplication by n map is literally multiplication by n. What do you think multiplication by n on the multiplicative group should be?
Maybe.
Yes? Ms. Alst, did you say something?
Yes, I'm saying t to the n, like just raised to the power n.
What are you raising to the n?
The variable, right? This t.
T to the n? Yeah, but you got to remember, you got to conjugate by translation by 1.
I see.
So you do that, and you get what you said. Okay. Again, so you see the drill. The multiplicative group is a little bit confusing because what you want to say is kind of what's happening at 0, and then you just have to translate it to 1 and then translate back. Okay. And so that's what this is. And you see that, so therefore, what is this? This is t to the n plus n choose 1, t to the n minus 1 plus dot, 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 dot. I'm writing it in the wrong order, I guess. And then there is no constant term because the plus n times t, right? So I'm writing it as I'm writing it as you usually write polynomials, which I guess it's a formal power series, so I should be writing it in the other direction, I guess. But luckily, it's commutative. Anyway, and so what's one point here? This is interesting. So this is true over an arbitrary ring. Why am I making this point? So you can see, for instance, that if the characteristic of R is positive, then the kernel of this map on the additive group the kernel of this map is multiplication by n. So yeah, on the additive group, this map factors through Z mod n. Okay, so in particular, right, because of course, if the characters, what am I saying? Sorry, so let's say the characteristic of R is equal to P, which is positive, and so this is what I mean. So in characteristic P, multiplication by P on the additive group acts as 0. Because multiplication by P on the additive group is just ordinary multiplication by P, basically, right? But what about this guy? These guys are all different power series, right? There's no way that none of these power series is equal to the 0 power series, right? And so if you're in characteristic P, just this universal map from Z into the endomorphism ring, it factors through the characteristic when it's the additive group, and when it's the multiplicative group, it's injected. Okay, so in some sense, this is potentially, and I think it is in this case, a non-commutative ring. But yeah, so the additive group has characteristic P, and the multiplicative group has characteristic 0. Okay, so again, what's the moral? The moral is that obviously it depends on which formal group law you choose, and it really depends in positive characteristic on which formal group law you choose. Okay. I don't need it, but there's a notion of, you may remember that in positive characteristic, there's the notion of height. So formal group laws cannot be isomorphic. All formal group laws cannot be isomorphic over a field of characteristic P, because there's this extra discrete invariant called the height. And the height, I'll just test, does anybody know what the height of the multiplicative group in characteristic P is? People who study Galois representations of elliptic curves should know what the height of the multiplicative group is in characteristic P. One. The multiplicative group has height 1. What's the height of the additive group in characteristic P? Hint, not 1. Take a guess, I insist. You must guess. What? I can't hear. Is someone saying 2 from like inside a washing machine? I can't.
Oh no, my tablet microphone is not great.
Oh,
I
okay,
have to use
sorry.
my tablet.
Are you saying 2?
P?
P. Oh, that's a good guess. That's wrong. It's infinite.
Oh.
Trick question. Okay. All right, so all of this, for instance, none of this is directly, it's relevant to what we're doing, but we don't need to talk about it. Okay. And then all of this stuff, the notion of the height of a formal group in positive characteristic, consult chapter. Now all of a sudden I'm taking this stuff seriously, and now I'm like, well, you should definitely read chapter 4 of Silverman's book now, because he gives a lot of information. Okay, any other questions? Okay, so here's a blank page in case I wanted to say even more about formal group laws over discrete valuation rings, and maybe I will later, but not now. Okay, so now we begin the Lubin paper. Okay, so what are we trying to do? Looks like we have enough for the beginning of our, I got a lot more where this comes from. We're not going to do it all today. So what am I trying to do? I just set everything up for you. So I'm going to take an arbitrary, R is going to be my, complete discrete valuation ring with finite residue field, equivalently the ring of integers of my local field. And I want to produce a one-dimensional formal group law, which canonically has the structure of a formal R module in exactly the sense that I just said. So I want a one-dimensional commutative formal group law over R, and I want it to have a homomorph in a natural way. I want to embed, in fact, R as a subring of endomorphisms of my formal group law in a very, very specific way. Why? because as I said, I'm going to base change to the separable closure, and I'm going to take torsion points on that. I'm going to take pi to the n torsion points on my formal group, and those torsion points are going to generate my abelian extensions. Again, the pi to the n torsion points on my Lubin-Tate formal R module is our generalization of roots of unity, if you want to say it that way. If my formal group law were the multiplicative group, then my pi to the n torsion points would literally be roots of unity. Okay. All right, so let's do it. Same old, same old. Local field, valuation ring R, maximal. The only thing to see here is that you notice I've chosen a uniformizing element. Okay. So here's the definition. Very innocent definition, not at all clear yet why we're making it. So f sub pi is going to be the following set of one variable formal power series over R. They're going to have no constant term, and their linear term is going to be pi t. So one idea is like plus higher order term. So you can think of this as being the linearized version of this guy. In other words, you drop all the terms of degree higher than 1 is just going to be pi of t. Okay, so this is a non-linear deformation of, yeah, I guess one way to say it is that if my formal group law were the additive formal group law, which it will never be, I believe that's not what we want in our application, then this would be this endomorphism. This would be multiplication by pi as an endomorphism on the additive group. We don't want the additive group, so we want some kind of deformation of literally multiplication by pi on the additive group. Okay. Moreover, we want different type of congruence. When we reduce everything modulo pi, getting a formal power series over the residue field, we want it to be congruent to t to the q. Okay, not really clear why yet. Okay, so by the way, this is definitely a non-empty set because there you go. Pi t plus t to the q is pi of t plus higher order terms, and when you reduce it modulo pi, you get t to the q. Okay, so definitely a non-empty set. Not the most profound comment. Slightly more profound comment. What if k is actually qp, so r is zp? Then I have an element that I really like in my f. If I take pi equals p, then how about this thing that I just defined? How about this thing which I just explained to you is actually multiplication by p as an endomorphism of the multiplicative group? You look at this and you say, awesome, multiplication by p on the multiplicative group is going to give me an element of fp. And this is the right way, right? So again, as I'm saying, I'm trying to define a kind of fancy formal group which has endomorphisms by R, and then the torsion points on that formal group are going to generate my abelian extensions. In the case where K is QP, it's not a fancy formal group. It should just be the multiplicative group, and therefore, the torsion points on the multiplicative group are really just roots of unity in general. Okay, so you can see how we're generalizing it maybe. Okay, so here's the absolute key proposition. I'll state it and maybe I'll deduce some consequences of this proposition. I think I do want to give the proof of the proposition because it's not that bad and it's used all over the place, but I think I would just have to rush through the proof too much to do it today. So here's the statement. I give you, let's read it carefully because it's kind of specific. So I give you two different formal power series that are no constant term, linear term pi, and then congruent to t to the q mod pi. I give you an arbitrary positive integer n, and then what is phi1? Phi1 is a linear form in n variables. Okay, so I mean, what do I mean? I mean it's literally a1x1 plus a2x2 plus ... plus anxn, just homogeneous linear polynomial. Then there exists a unique deformation somehow of this linear form. So there exists a unique formal power series in n variables such that, well, it has no constant term its homogeneous linear term is precisely the linear form that I started out with, and then it has higher order terms. So again, this one is just saying it's some nonlinear deformation of my linear form. And then it kind of has this somewhat generalized homomorphic property, okay? So if you do F composed with phi, then that's the same as doing phi composed with g of x1 all the way up through g of xn, okay? So in a special case, if phi were you know, a two variable power series, then this really would be building a formal group law. This would be building a formal group law, and if F were equal to G, that would be giving us a homomorphism between them. So this is a little bit general, but you see it's a kind of anyway. So a unique formal power series, which is kind of has this homomorphic property between F and G. And so yeah, I will abbreviate this homomorphic property with respect to F of G as F composed with phi, which I think is totally reasonable, equals phi composed with G, which is not really reasonable. Really, so Harari for a little while writes this as phi composed with G. Okay, that's what it really is. And then later he's like, you know what? I'm just going to write phi composed with G. So I'm going to do the same thing. Okay, but again, phi composed with G, you type that into your computer, it's not gonna like it, right? Unless n equals 1, because phi is an n variable formal power series, and G is a you know, and G is just one formal power series. So what else would I mean? Anyway, by phi composed with G, I really mean this. Okay, so this is the key proposition. This is literally the first thing that Lubin and Tate prove in their paper. You can probably imagine that we're going to prove this by some kind of successive approximations. Okay, so that's I'm going to skip the proof for now. Maybe I think I'd like to come back to it. Okay, so that's the proof. It's, you know, it's not nothing, but very self-contained. Okay, so skipping the proof just for the moment. Let me kind of maybe this result and its proof will be a good place to stop for today. So right, so here we go. Now we're going to get the construction of the Lubin-Tate formal group law, really as a corollary of this proposition. So I take my F as above. The theorem says there's a unique formal group law that, fortunately or otherwise, we call capital F sub little f, such that F is canonically an endomorphism of that formal group law, okay, which means exactly this. Okay, we're going to build more. We're going to see that the next result is going to be that for this Lubin-Tate formal group law associated to F, actually we're going to get formal R multiplication. So we'll do that. It follows pretty easily. And in fact, in the light of day, this F is going to be multiplication by the uniformizer pi as an endomorphism of F. So that's what it actually will be. But at the moment, first of all, we need a formal group law, slightly fancy formal group law cooked up out of this one variable power series. And how do we do this? Well, we just had a proposition that's very general that we can apply to any linear form whatsoever, right? So this proposition is not tricky at all to apply. You just give me a linear form and some number of variables, and then boom, there's some formal power series that, you know, is the linear form plus higher order terms and is FG equivariant in this sense. Okay, so in the application of this proposition, which we're now going to make several times, well, once today and then the next one later, the question is, well, what linear form should I choose? Well, hold on to your hat. I'm going to take phi1 to be x plus y. Okay, so n equals 2. Phi1 is going to be x plus y. I'm going to take f equals g because I want an f equivariance. And then according to the proposition, there's a unique formal power series in two variables, which starts out x plus y plus higher order terms. That's very promising, which is ff equivariant. Well, awesome. That's exactly the homomorphism condition. Okay, so I'm done, except I need to verify that this phi, so my ff is going to be my phi, my unique phi, given by this proposition, but I still want to check that it's a formal group law. Okay. So I know that it's F homomorphic before I know it's a formal group law. So now you have to remember what do we actually have to check to get a formal group law? It would be enough to check that it's X plus Y plus higher order terms. Okay, that came out of the proposition, right? And then we just need to check the sort of formal associativity. And as I've stated to you as exercises, the other two properties follow automatically from those two properties, and the commutativity is going to follow because R is a reduced ring. Okay, how do I know the associativity? I'm going to use the proposition again. So this is kind of cool. And so the idea is I claim I have these two different, it's funny, I have this one guy phi, which is f of fx of y comma z. I have this other guy phi, which is the composition in the other direction. I want them to be the same phi. What's the idea? The idea is that they're both going to be solutions to this proposition where there's a uniqueness statement. Okay, so this guy and this guy are two formal power series deformations of the same linear form in 3 variables, which is just x plus y plus z. Okay, so in order to prove the uniqueness from the proposition, you just have to convince yourself that that both of these guys, I mean, they certainly do satisfy x plus y plus z plus higher order terms, because this one is x plus y plus higher order terms, you know, et cetera. So that one is clear. And then you just have to check that that these two guys are both of these guys are F homomorphic in the sense that, you know, this thing, if I put F's on the inside, then I can pull them out and get F's on the outside. And that is literally just a 2-line calculation that I invite you to do. So using nothing, just using this homomorphic property. Okay. Maybe next time, maybe it's better if I write. It's so simple. If I get next time, maybe I'll just write it out for you. If you don't want to do it yourself. But yeah, so the associativity is also following from the uniqueness of this proposition. So this guy, this associating this way and associating this way, both of them are 3 variable power series whose linear part is just x plus y plus z, big surprise, and they're both F homomorphic. So by the proposition, there's exactly 1 power series that has both of those properties. Okay, so we're leaning on this proposition is the key to all of it. It's the uniqueness is, we're using the existence and we're using the uniqueness heavily. Okay, and I think that's probably a good place to stop. So yeah, so here for every f and f pi, we associated the Lubin-Tate formal group law. Maybe I'll just show you the next theorem, and this is where we're going. So the next theorem is, I take this associated Lubin-Tate formal group law. There's a unique formal R module structure, which again is a ring homomorphism from R into the endomorphism ring of this formal Tate group law. With what properties? So for every x and r, I'm giving you a certain endomorph, just the image, I'll just call this, yeah, so homomorphism is called bracket. Okay, so what properties does bracket x have? Bracket x is a nonlinear deformation of literally just x times t. That's kind of what you probably were expecting. And bracket pi is the f that we started with. Okay. So it's a little bit funny. We give ourselves a polynomial, 1 variable power series rather, that has a couple properties, and then we reverse engineer from this polynomial. There's a unique formal power series which has a unique formal R module structure, so that multiplication by pi is precisely the 1 variable formal power series that we started with. Okay, well, you know, that's where we're going. So these are, I told you I wanted a formal R module structure and blah, 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 blah. So we're on our way. Okay, so next time, I suppose I might change my mind, but yeah, to be frank, this proposition feels kind of basic and satisfying. And then I think some of the later verifications are going to be more technical. So I think I'm in the mood to give you the proof of this proposition and skip some of the slightly more technical things that come later on, but we'll see. Okay, any last questions? All right, well, I said I would do Lubin Tate's approach to local class field theory, and are we not doing Lubin Tate's approach to class field theory? We are. Okay, so we'll continue next time. See you.